All right, so what we're doing for like the first 10, 15 minutes of class is we are finishing our sticks and spheres lab. I know if you're at home, you don't have this. So anyway, I will stop and then we'll do the rest of the things, homework problems 37 through 42, and we'll be off to the races. All right, well, magnesium's a metal, so it makes the positives. So we got N here, Mg times 3. You all right with that? Thank you. The dots, I'll draw it a little bigger so you can see it. We'd have an N. Man, what's wrong with my throat? And then we have an Mg. N had 1, 2, 3, 4, 5 of its own. 1, 2, 3, 4, 5 of its own. Magnesium shares 1 this way and 1 that way on all of them. And that is the way we complete the octet. Magnesium got none, magnesium got all. Okay, so we would call this magnesium nitride. Whoops. All right, so lots of things we're supposed to sort of reinforce here. Every model, every number should add to 0. That's because ionic bonds, everything always adds to 0. We were supposed to reinforce that the metals become positives, the nonmetals become negatives. We sort of reinforced the idea that the nonmetals get all the dots, the metals get none. We introduced the idea of how to name an ionic compound. We name the metal, we name the rest ending in "ide." So nitrogen becomes nitride. We hopefully reinforced that something from family 1 are the plus 1s, family 2 are the plus 2s, family 3s plus 3s, and then -1, that's family 7, -2, that's 6, -3, that's 5. Like lots and lots of stuff on there. Okay, hopefully you feel all right about that. Let's wrap up something that I thought we'd wrap up the other day, but we just definitely ran out of time, and that's the homework. So have your periodic table out, and we'll sort of combine a little bit of what we just did. Oh my. Wow, I just had this feeling I needed to get up. It was nice never having you in class. I was worried though. Okay, no problem. Kayla. Probably yearbook related. All right. So, electron dot structure. Let's do these pretty quick together. So would you tell your partner, how many dots do the nonmetals get? Tell your partner, how many dots do the nonmetals get? No, the other way around. 2 zeros on top of each other. They get 8, right? Now, you ready? How many do the nonmetals get? No, 0. We're good. All right. So what you do for the dot structure here is you just literally put K, whoops, pen, K, O, K, just like it is right here. And then you put 8 dots around, hold on. I don't know why it does this sometimes. You put 8 dots around the metal and none around the nonmetal. I said that backwards. 8 dots around the nonmetal. 1, 2, 3, 4, 5, 6, 7, 8. And then 0 around K. And that's it. Okay, how would you determine the type of bond? Tell your partner real fast. How do we determine types of bonds in this class? Subtraction, and then you yeet it. All right, so just a quick review. The type of bonds, we would find potassium and oxygen and do the math. Did anyone else do it a different way? Oh, Tom. Did anyone just read it and say, hey, that's a metal and a nonmetal, that's an ionic bond? If you see a metal and a nonmetal, it's always ionic, or do the math. So we had K, I almost forgot what we even had. And O, so I take big 3.5 minus 0.8, 2.7. Then I compare that to my periodic table and it tells me it is ionic. Oh man, we're kind of quiet today. Thank you, whoever that was over there. Why is this not working well? Ionic. And then all of these questions come from that top right corner of your periodic table. Will you finish that row real quick so I can double check you know what we're doing? Curtis, you got your periodic table out? Oh, you are the man. Blake, you doing all right today? Okay. Staring out the window? Okay. Oh, okay. I thought I was dead. I thought I was dead. Did you cheer last night? Was that weird?
Yeah, it was awkward.
It was really awkward.
And then like this when we had to like do something, like I played a lot and I was just like, oh, everyone heard that.
I don't know. We got to do something.
I know. Mrs. Cat was telling me that she wants to take Chromebooks and just have like this like Zoom in except for Chromebooks and the bleachers. So I was like, and then she wants to make like the cheerleaders with her because we can only have 10 there, but she wants us to be like during halftime do like the free throws for like the kids on the front.
So where I make fun of people?
Yeah.
Okay. I can do that. I love making fun of cheerleaders when they shoot.
It's pretty easy. We're not good at it.
Well, you're not dressed for success. Let's be honest. For shooting a basketball, a pencil skirt's not the best idea. I don't know if it's a pencil skirt, but essentially it's not athletic wear. Okay, here we go. Does, everyone shout it out with me. We'll just have a party here. Does KOK dissolve in water, hexane, both or neither? Water. You guys are great. Will it conduct when it dissolves? Yes, it will. Does it conduct in pure form? No. High, medium, or low? Hello. Thank you. I was saying hello in case you wondered. Oh, no, I'm dumb. Brittle, malleable, or neither? Oh, I almost wrote malleable. Good thing that little M turned into the line for the B. That was perfect. Okay, not super hard. Okay, I will just do the dots with you and then you fill in the rest here in a minute. BaCl2, very similar. Cl, BaCl, 8 dots around the non-metal. So this time the dots are around the outside atoms, and that's fine because those are the non-metals. All right, this is carbon dioxide right here. This one's a little different because all of them are non-metals. So see how there's 2 lines here? That means there's 4 electrons between them. But carbon now has 8. Oxygen has to be fixed. So you put the other on carbon. So if you look, each one sort of independently has an octet, even though really none of them had an octet. They all feel pretty happy. Kind of makes sense? We'll learn about that. That's a covalent bond. That's in the notes here in just a couple minutes. Okay, Br-Br. Both nonmetals, so they both get 8. The one line in between represents 1 pair between. And then ammonia at the bottom. And H3, N gets 8, H gets 2, and everyone lives happily ever after. All right. Can you help me on 41? It's aluminum, aluminum, aluminum. What do we say when we have a bond that just has a bunch of the same metal? It's a metallic bond. That does not look very good. Whatever, that says metallic. All right, this we haven't talked about, but if it's two nonmetals together, then the difference is 0. So we'd say this is a non-polar. Okay, you can do the rest of them pretty easy. So let's take 6 minutes. See if you can fill in all that homework. This arrow's just not really going my way. We're going to record from now on. The first thing that's really important to know about covalent bonding is that it is super different than ionic bonding. Like, we've learned all these rules. I think that most of you feel pretty good about your knowledge about ionic bonding, but now we're going to throw in a different one with different rules. So it would be like our good friend Ashlyn over there. She spent, I don't know, 5 months playing volleyball in a row, right? All right, so then just boom, 2 days later, you now have to play basketball. Do they have the exact same rules? No. All right, they're super, super different. I've never seen a volleyball point scored with the volleyball going through the basket. That'd be pretty cool, wouldn't it? It'd be hard, really hard. All right, I've never seen anyone take a charge in volleyball. That'd be fun. All right, but they have two completely different sets of rules because they're two different sports. All right, when we talk about ionic versus covalent bonding, please realize they're like two different sports. They're similar, like there's a ball involved, like the electron, but everything is pretty much different after that. So you already have this filled in, I'm sure, but atoms with the same or nearly the same electronegativities, that's the longest word of the year. Hope you enjoyed writing that, tend to react by sharing electrons. And it sort of makes sense. If Kieran and I were going to arm wrestle over something, but we were pretty close to the same strength, it'd take a long time to arm wrestle. In an ionic bond, it would be Kieran's just ripped and I'm a wuss and she just takes the electron. Like, I have no choice. It's just stolen from me. But when they're similar in strength, they have to share. And so that's when we get two nonmetals reacting with each other. So here we go. The shared pair or pairs of electrons constitutes a covalent bond. So when we have hydrogen, we know it's diatomic. We learned that a long time ago. It had a little 2. And that's because when hydrogen is alone, it only has one valence electron in its outer shell, but it desperately wants a second one. So what it does is it finds a second hydrogen and they share. We'll put the second hydrogen, it's 1s, but we'll just draw it to the left and we'll put it right there. So they mix their valence electrons to fill shells. When they share valence electrons, we call it a covalent bond. Now, this usually occurs between nonmetal atoms, and they are bonds with differences in electronegativity that are less than 1.7. So 1.7 is pretty much the cutoff for where an atom's not strong enough to hold on to an electron. If you're above 1.7, you will lose your electrons. So pretty much in an ionic bond, the metal's always low, the nonmetal's always high, and we have this big difference, and that severs the relationship. Covalent, though, since there's small differences, they have to share. All right. So here's just another example, just illustrated. Fluorine has 7 valence electrons, but it wants 8. So each fluorine, they decide, well, the best thing for us is if we just share one pair of electrons. So they come together, they share this pair, and that now gives both fluorines a simulated octet. So even though they don't have 16 total electrons, they can pretend they do if they share 2 of them. Okay, fluorine itself had 14 if you multiplied it by 2, because this had 7, this had 7. They had 14, they want 16, so they have to share 2. Kind of okay with that? All right, if we have O2, that's what Shaylin asked me a little bit ago. Why would it have to share 2? Well, they want 16 total valence electrons. If there's 2 of them, they always want 16. But each oxygen only has 6. 6 plus 6 is 12. So they have to share 4 of their valence electrons. Does that help at all? So they come together and form a double bond. All right, nitrogen will do the same thing. Nitrogen has 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. They both want 8, so they want to get 16. They only have 10, so they have to share 6 electrons. So nitrogen forms a triple bond. So this triple bond is really, really strong. In our atmosphere, every time we take in a breath, 71% of that air is actually nitrogen. And when we breathe it in, it does absolutely nothing to us. We don't have a gain. We don't have a loss. The nitrogen goes in and it comes right back out, because in our lungs and the exchange between our cells and our blood cells, we don't have a chemical that can break this down. But the O2 is less strong. We can definitely break that down. All right, and that goes into our blood cells. That gives us life. Now, this one, fluorine, is like so unattracted to each other that if we breathe this in, it will steal electrons from us and it would kill us extremely quick. If you breathe this, you would die within 10 minutes at least, maybe even faster. Not trying to be depressing, just trying to be edgy. All right, now, it turns out, what time are we out of here? What? 26. Okay, those people walking by kind of freaked me out. It turns out that no 2 elements have exactly the same electronegativity. I should put a little star up here. And then it would be like, unless they are the same element, like the previous 3, but that's okay. So we're going to learn that even though they share, they don't always share equally. So just going back a slide and inserting one here. We have covalent bonds, which means that they share. We have 2 types of covalent bonds. We have polar, and I think I already discussed this a tiny bit, maybe I didn't, and non-polar bonds. So both of these share. In a non-polar covalent bond, they share equally. And then a polar bond, they share unequal. So just kind of, this is the basic idea between the 2 that makes them different. Polar, they do not share equally. Non-polar, they do share equally. Okay, moving on. Oh, look at that, I had it. Okay. Because of this, when covalent bonds form between 2 different atoms, one of the atoms more strongly attracts the valence electrons of the other atom. So what we commonly draw when we talk about polar substances, that was a really good O right there. Then I choked on these, but whatever, is water. Oxygen's electronegativity is a 3.5. Hydrogen's is a 2.1. And remember, electronegativity is how attracted the electrons are. So the electrons that are shared right here, instead of, that was just dumb, why did I put them there? Instead of being shared completely in the middle, they're actually shared, but that was great. Puberty, 35th year in a row. They are shared, but most of the time they're by oxygen. So oxygen's like, hey, let's share these, but then it like really mostly takes them. And you've probably been in those friendships before. Like, hey, we're friends, but I'm going to ruin your life. You're like, oh, it's okay. Like, I don't know. There's some benefit there. And hydrogen gains some benefit, but it's unequal sharing. This is why water is polar. We say that the electrons move that direction, which leaves hydrogen slightly positive. And if hydrogen is slightly positive, then the oxygen must be slightly negative. So then what we define as something that's polar, I don't know what's going to go here, but there we go. Polar simply means two-sided. So water has a two-sided molecule. It has a negative side, and it's really this half, and it has a positive side, which is this half. So since it's not sharing equal, it makes a two-sided molecule. Okay. This unequal sharing of electrons causes one atom to be more negatively charged and the other more positively charged, resulting in a polar bond. So in this picture up here, which one of these, green or blue, is the more electronegative atom if the cloud is representing where the electron is most of the time? Green, good. Which one said that? Good job. The green is the one that's more electronegative. So we'd say like this is oxygen and this would be hydrogen. The electron will reside closer to oxygen more of the time. That leaves this side's nucleus exposed, which is just a proton, and it puts a little bit more electrons on this side. So once again, we end up with a two-sided molecule here, one side positive, one side negative. That is unequal, so we call it polar. Now, an example of a polar relationship was when I was a sophomore, my sister and I shared a car. Did I already say that? That was you last year, wasn't it? Or did your sister graduated 2 years ago?
She graduated, yeah, last year. We're still sharing her.
Okay, how did that go? Did you share it equally?
No, because I never get it. She works.
Boom. There you go. When I shared a car with my sister, let's do some math here. There's 180 school days roughly. I got the car once, which means she got it 179 times. Now, did we share that car? According to my mom, we did. But according to my older sister, we hardly shared that car at all. It was hers. She had had her license for 2 other years and I was a loser. All right. So we were supposed to share it and we sort of did, but it was more by definition. In water, we have our older sister would be here. And this is sad that Megan's not here because it was her mom. This is Amanda. This was me. That's Tom. What are the odds? Megan doesn't come today. I'm going to make fun of her mom. But it was only sharing by definition. In a polar bond, we only really are sharing by definition. Did I skip something? Uh-oh. What are you missing? Oh,
Is it same?
in a covalent bond. Maybe that was deleted. Did you have that? Okay, I must have deleted that side. There can be a sharing of 1, 2, or 3 pairs of bonds in a covalent bond. David. Yes. Yeah. We're good. Thank you. All right, my friends. Oh, I This is the second time this week I've almost said, have a great weekend. It's Thursday. Here's the depressing part. Last time it was Tuesday. But after we have fun in this class tomorrow, we'll have a great weekend, right? Okay, you guys are awesome. I really do enjoy this class quite a bit.